It's like bark, 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 bark. What's that, Lassie? Someone stuck in a gravitational well? We all are. That's funny. Does Eric ever talk about things that aren't about time? So listen here, everybody. Okay? This is not my fault. Okay? Admiral Entropy had got me thinking about some stuff. He gave a couple papers on the Discord. Everybody should be on the Discord if you're not. ! Discord. And he gave me a couple papers and a couple ideas that I've been thinking about a lot lately. I think about time a lot always because it's what I study. Okay? So I study that. My physical research project is about time. Okay? And okay, so that's all set. If we do die, I have this one for backup. And then so I usually think about time frequently, but maybe in a less philosophical point of view, and maybe in a more like mathematical point of view. And Admiral Entropy put a couple papers in Discord that really got my like philosophy gears rolling with time again. No, it's so obviously if you're a part of this community, you know that I study time a lot. It's definitely my thing. And it's one of those weird fields of physics that like it's not mainstream, but it's sure coming into it pretty quickly, isn't it? You know what I mean? Like you see it all over the place now. It's really weird and exciting for me, obviously. But like when I wanted to get back into physics and study something, I wanted to study time. And when I was first looking into it, it was not at all popular. But the past like 5 years, it's really starting to come out of the woodworks and get really popular again. So that's exciting. Let me ask you a question. So how many people in here, let's run a short poll, okay? How many people in here have studied, and I'll set it up there, mods. Thank you very much. Studied QM, quantum mechanics. How many people have studied quantum mechanics in a college setting or a personal setting, like working through textbooks or, and I kind of mean formalism, but not necessarily, just you can answer that however you feel like. So let me explain to some people, especially because we have over half knows already in the poll. So let me explain to some people what quantum mechanics is. I'm sure most of the knows know what quantum mechanics is, but let me just explain it really quickly. Quantum mechanics is basically the mechanics that governs the motion and the behavior of the very, very small. Okay, so that there's like thresholds of like size and stuff, but really quantum mechanics is a probabilistic scheme. Right, you set up a scheme probabilistically, and it happens to be the scheme that best describes very small things in such a way that we have things like the uncertainty principle, where you cannot know a particle's exact position and exact momentum at the same time. The laws of quantum mechanics forbid that. Whereas if I were to just say, hey, this coin right here, I'm going to flip the coin in the air, while it's oh no, I almost lost it. While it's a probabilistic coin, you can still govern the motion of it. You can still figure out the momentum and the position of it as it goes through its arc, right? And that's because it's classical. You can see that. And at some point, the physics of this changed to where that gets kind of more and more hazy. See, up was uncertain there. It's true. Whether or not I would find it afterwards was uncertain. And I think there's like a rough, so I've heard of rough estimates of when the mechanics really become like quantum and when they don't and things like that. Now you can describe classical things probabilistically, but it does get, but there is some subtleties with that. But for the most part, especially for like your year 1, 2 of quantum mechanics, we say that there's, the small and the large have different properties, right? And the idea behind the probabilities and the uncertainty things in the uncertainty theory is that we cannot, like I said, we cannot know both the position and the momentum of a particle that behaves quantum mechanically like we can of a classical particle. So that's the idea. Okay, so let me ask the question. I think it was 14 said you did study quantum mechanics. 18 said no, you haven't studied quantum mechanics. Here's my question to everybody, and I would like, and you guys can answer. This is your time to talk to, to me or whatever or whatnot about how you feel about this and to each other. We have a very talented physicist in chat that I know of, so this is a good time to talk to each other as well. But what was your experience with time in quantum mechanics? Is the question. we talked a long time ago on stream, and I put it on YouTube, about the uncertainty principle. One of the uncertainty relationships that we talk about in that video, but not in depth, but just sort of mention, is times as clocks have this weird observable principle, right? Like we can observe time as a clock. We can observe time as a clock, and when I say that, what do I mean by a clock? I mean a physical change, right, in something, i.e., and we talked about this with radiation last time, where we did radiation in to prepare for the cloud chamber that we're going to build in a little bit, and we also talked, I think it was the week after, about a piezoelectric crystal and how that works inside of quartz clocks, right? Those are the oscillations that happen, whatever it is, 32,768 times or whatever per second, but every second the crystal inside of a quartz watch vibrates that at that speed when you put voltage into it, you know? Like those are events that happen, right? And they happen in a consistent way, and we can keep track of those, and those are what we call a clock. And like you can call that clock whatever you want, but it's really going from one event to another event. So, let's see, what do we have in the chat about time and quantum mechanics? Understanding I have is of time being absolute within quantum as opposed to relativity. Very good, Tartan. And we'll talk more about that too. The idea, yeah, actually that's kind of like the main thing. So you kind of hit the nail on the head with that one. Admiral says, I have about 22 papers on my hard drive about time and quantum mechanics, not to mention another bunch of closed time curves. It's a fun subject, but these things never came up in any formal class. There we go. Why can't we know? Because it's too small to track and see, or because we don't know the math? I think it's more along the lines of we don't know the math for the actual physical outcome. That's my own intuition. However, the math is correct, and it might be that my physical intuition is wrong. Like, we want our physical intuition to be classical, but there's a good reason to believe that our physical intuition is the thing that's leading us astray, right? That our physical intuition has evolved in a way that just sets us up to see things with definite momentum and definite position. But there's no reason to say that that's the way it has to be. It's a category. Oh, there we go. Justin has a good point too. It's neither. It's a category error to ask the question. So that's the. It's like asking if science. That's a good point. It's like asking if science is failing us because we don't know what blue smells like. Interesting. That's an interesting point. Let's see. Bumpoof says, when time is stopped and started again, would we notice? Okay, so that's a great question, and it completely depends on what you think time is. Okay, let's be a little bit clear about this. There's two interpretations of time. And we're not sure if either of them or any of them are ultimately correct. Okay? There's a presentist version where the only thing that exists is the here and now. Nothing else exists. So things just change, and then whatever happens in the future, whatever happens in the past, it doesn't matter. It's not a thing. Okay? So the thing that happened to well, let's not get too far into it. But that's a presentism. That's the only thing that ever exists is just the here and now. So therefore, everything else that governs the dynamics of the universe, and presentists are pretty good at what they do, and they have ways of handling almost anything you can throw at them, except one thing that they struggle with is the laws of special relativity. Okay? Now you can say that special relativity is just correct and that's it. The second idea is called eternalism, or black universe. And this is the one that I would say most people subscribe to in the physics community. And that is where the past and the future exist, okay? And we are just observers going through this dimension of time, right? In the four-dimensional space-time. This one is much more intuitive to what you might think would happen if you were to stop time. Okay? So in this situation, time is just it's just a coordinate in four-dimensional space. So it makes things a little bit more intuitive when it comes to things like stopping and starting time again, right? Because it's just a coordinate. So if you were to just stop time and space and then just start them up again, it'd be the same thing as stopping in 3 dimensions of space and then starting up again in 3 dimensions of space. So when you walk up, like down the sidewalk and you just stop, your spatial dimensions in your locally, of course, like Earth is rotating, Earth is orbiting, the solar system's orbiting, all this other jazz, whatever. But like locally, you have stopped, okay? So your 3 dimensions of space are no longer changing, and your time is still changing, right? There's no reason to believe that that there could be a reason to stop and start again. However, we know that doesn't happen. Why does that not happen? That's something that physicists like myself continuously want to know and continue to work on, is why time won't stop. Why locally we can talk about space stopping, but locally you cannot talk about time stopping. Time does not stop locally. Time does not go backwards locally. Time moves forward always. What about memory? Is that not visiting the past? So no, because it's just something that occurs inside of your head. It's something that occurs inside of your brain. Now, there's some sort of implication on the influence of it, but that doesn't necessarily mean there's anything present about it. So presentists always think that time just emerges out of change in the present, right? So one thing, like an event an event moving from event 1 to event 2, be it whatever it is just a series of events happening under some sort of rules. Now, you might think like, hey, this presentist viewpoint is strange if you want to think about anything other than kinetic terms, right? Kinetic terms are about the now. Kinetic energy determines the energy of the now. But what about potential energy, right? Potential is strange. Like potential energy is about the future. It's about how much energy your system could gain or lose. Right? But presentism is fine with that. It can handle everything perfectly fine. It does not need to have some sort of time where things unfold. But yeah, so memory is well and good. Memory is just your event has a process where it knows events, and recalling on events doesn't say anything about the event itself. It's a processing for the event that happened now. Or the events that are happening now. You're just more processing. And that's like a weird thing because like Haney said, it's memory's recording, right? And you tapping into that recording to influence the decisions or the choices that you're making right now is not going back in time. It's thinking about the events that have happened and adjusting your current decisions to use that memory. And memory is one of those things. I still say that time is just a language. The way we describe the observable change is just like math's language to me. And that's an excellent way of saying it. Let's be real about something. And I've always kind of thought this, but I think Sean Carroll kind of gave me the confidence to say this phrase, right? And time is real, okay? Let's be very, very clear about that. Time is real. It's a real thing. The question that we need to ask is it fundamental? Or is it just emergent? Is it just, and like what Sarah says, a language might be perfectly fine because quantum mechanics is just a language as well. It's a language that describes the little things. So time is an illusion. Time is actually not an illusion. You should not, please, if you're in this channel for long enough, you should not leave thinking time is an illusion. It's a very real thing and it has real consequences. The issue is it more fun? Is there something more fundamental? Quantum mechanics is a probabilistic mechanics. Right? There is a series of probabilistic. It is I was it on the heater? It has probabilities in measurements, right? Like you cannot measure the same so quantum mechanics. Let's get full circle here. Quantum mechanics has this property where states the descriptions of particles. Well, you can be in multiple descriptions at once. Okay, let's be real about that. And this is all the mathematics, okay? I'm not saying anything about the physics. I'm saying about the mathematics. You can be multiple descriptions at one time, like spin of a particle. You could be both spin up and spin down, and spin is not a ball spinning. It's not this, okay? It's not spinning. It's a quantum number. It's a description of a particle, like a mass. You can be in both of them at once, right? And then measuring them, you always get one outcome. You never see both of them at once. You always measure them and see one outcome. And that one outcome follows probabilistic rules. What about before that? What about before the measurement where the math tells us it's both? It's in both quantum numbers. Okay, so yeah, so we have to be very careful about the ideas of what's going on before a measurement. And then once you measure something quantum mechanically, then can say it's classical, it's not, but we can find a definite, we can find a definite spin for that system. So we'll keep it kind of, I'll keep it kind of like stuck at where I'm at. So Blayman says, math is also philosophical, right? Does it exist outside the brain? I would say it has to exist outside the brain almost by the nature of it, right? And the nature of it is kind of like how we've defined math to be something that exists amongst all of our brains, right? Like there's some bit of math that exists in my brain that I can also transfer to your brain, and you can then, use however you want. I feel like if it was internal, then there wouldn't be a way to transfer it to, someone else. So math is philosophical. Does it exist outside the brain? Because we can use it equally, I would say yes. Now the question is, so like let's use a. Oh, I want Miss Admiral stuff either. Hold on. Let's say, can red exist, or is red a construct of the brain? Right. Now you might say to yourself, red doesn't exist, right? Why? Because you don't know what property red might have. But the reason being that I would say it does exist is because we can all say that red is the same thing. And what I see, how my brain detects it, and then, my eyes detect it, my brain detects it. And now, of course, colorblind obviously changes, blind, whatever, we're talking about unimpeded circumstances, right? So this is red, right? Now, whatever color this is, as it's moving through my eyeball and hitting the back of my eyeball and then transmitting information to the brain, there's nothing that says, philosophically, that this means that this is the exact same color that you see, right? Your red could be my blue. My blue could be your red. That's not the point. The point is we can use this as a language of description to describe this object. And the math is the language that we use to describe things we see in the universe, right? That would be what I use. And then you can do other things like that. You can extrapolate. I can extrapolate a different color that I might have never seen before. We'll call it pony red, okay? And pony red could be an extrapolation where I induce different things, commentator, where I can, extrapolate a different color based off of what I know red to be. And then, I'll call it pony red, and you can say, oh, okay, I'll call that pony red too. And then from then on, we know it's pony red, right? Let's see, what did Admiral say up here? Any time-dependent solution of the Schrödinger equation can be made into a solution of a time-independent by entangling it with a clock. Time is an illusion. Time is not an illusion. I guess the question is it fundamental? And from the quantum mechanical point of view, I would say, no, it's not fundamental. Now, I would like it to be fundamental. I would like the quantum mechanical time to be fundamental, but I don't think it can be in quantum mechanics. Quantum mechanics time clocks have to evolve out of the system. So here's the deal. Here's the thing I was getting back to, kind of getting back to a couple of what people said earlier and things like this is finally the thing that I'm trying to get to. And then we'll do our calculation about time in a gravitational well, how we using general relativity just to further screw you up. Why these things matter. This is the great conversation for explaining why these things matter. Is that Newtonian mechanics uses time as a parameter, okay? Not a spatial dimension. It's just a parameter. Just run it, okay? Now, special relativity comes along. No, general relativity even stronger. No, time is a coordinate, right, in space-time that we can use to describe vectorially a place. Vectorially just means a description in a vector space, which, we can call space-time a vector space. Now, but it's just, it's a description of a point in the space-time. Quantum mechanics does not make clear what time is inside of it. I think it's wishy-washy. I think it uses a vector representation if it wants. It uses a parameter if it wants. And this paper that Admiral Entropy shared with me, if you have some quantum mechanical background, you may find this very enjoyable, as I did. time dependence in quantum mechanics. I'm still working through it. I read a bunch of it, but I want to go through it more detail. Let's not put it there. It has a good explanation of how this shows up, how this rears its head, right? If time was an illusion, why does time change in space? Exactly. Oh, wait. If time wasn't or was an illusion, why does time change in space? And that's, I think, is exactly... I think that's exactly the thing that we need to have to continue to study in that. And so if you are new to the stream, I study time in a way where, in a very pragmatic way, practical way, where I am trying to understand how we use time in a quantum computer. And I'm curious about how it behaves inside a quantum computer, because this whole bit about quantum mechanics and using time as a parameter for some and an observable for other things, it's like, when are we going to actually do it? To sum up the discussion of what we just talked about, before we go to the board and actually see some of this stuff in action, excuse me for the microphone stuff, we have a system of physics that has entropy, energy, time as a parameter, time as an observable, time as a coordinate in space-time. We have temperature. We have, which is, not fundamental, which is emergent from things like kinetic energy, interactions. All of these things happen, and all of them are time-related. How does one learn all of these things? A long time of studying. I've been working, when I went back to school for physics, I was 28 years old. It was 2016, the fall of 2016, and I have been working on time literally since I started. And I'm very, 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 very far from doing anything worthwhile. The people who have made big contributions to time, physics, have been, are usually people who have been working on it for a very, very, very long time. I can make time disappear somewhat. Stay in isolation, it will blur. So, blame me. You might, if you enjoy that type of stuff, you might enjoy looking up the work of Lara. I think it's Lara. Lara Boroditsky. Like this. Lara Boroditsky. She has studied this in depth. And it's one thing that I find very important when you study time, because it's been over 10 minutes since I said I would stop. Because in the underground thing, I don't know. Because she has studied the way that people perceive time. Oh yeah, Sarah, you would like it a lot too. Yeah, you would like it a lot too. People perceive time differently in different parts of the world. And she goes through and goes through, like, some people, some tribes in Africa. I think it was Africa. Maybe it was Australia. No, it must have been Africa. It was, what was I gonna say? Oh yeah, they perceive time like a river. And some people perceive time directionally, north, south, east, west, directionally, like that direction, right? So it's just, she has great ideas in about that type of stuff and has put in a lot of work.